Yes, welcome everyone. I'm first have to announce that our first speaker unfortunately is not available, so we directly start with our second speaker, Johannes Thürauf. But still, I'm very happy to introduce him and having him here. So he's a postdoctoral researcher at the Trier University. He studied mathematics at the university in Erlangen-Nuremberg and also received his PhD there. And his work is mainly focused on robust and bi-level optimization with a lot of application to networks, gas networks, and so on. And very happy to have you here. Please, the floor is yours.
Thank you for the nice introduction, and also thank you for the great opportunity to give a talk here in the seminar. And today we will talk about adjustable, robust, nonlinear network design under demand uncertainties. And this is joint work with Julia Grübel and Martin Schmidt. So the main task today is that we want to compute a network design taking into account demand uncertainties. And while we do this, we will consider a very accurate non-convex transport model for transporting the demand scenarios through the network, which will then lead to an adjustable, robust, mixed integer nonlinear optimization problem. So a very challenging, robust optimization problem. And the main challenges are that we have discrete decisions and nonlinear constraints. So we cannot apply any standard techniques of robust optimization, such as like strong duality, for example, because we really have here non-convex constraints for our adjustable decisions. And the question is now, how will we tackle these problems? And our main ingredients and key components to derive a solution approach will be that we want to exploit the underlying network structure and structural properties of our considered flow model. And for this, we will consider so-called potential-based flows. So the guideline for today is that we will first introduce our flow model, then we will move on to our robust optimization model to compute the robust network design, and then we move on to our main result, which is that we can verify robust feasibility using polynomial many worst-case scenarios. And then I will present some computational results. So, but first we will start with our flow model. And for this, we will consider so-called potential-based flows. So we'll have a network that we model by a D-graph consisting of nodes V and arcs A. And the nodes are partitioned into nodes where we can inject something, nodes where we can withdraw something, and so-called inner nodes. And then we consider balanced load flows L. So a load flow represents the injections and withdrawals at every node of the network at a single point in time. And these demand scenarios have to be balanced. So the total amount of injections is equal to the total amount of withdrawals, because we consider stationary flows. And then we say that such a demand scenario is feasible. That means it can be transported through the network if we have flows Q and potentials P that satisfy the following constraints. So the first two constraints are the classic flow conservation and lower and upper arc flow bounds that you know from capacitated linear flow models. And then in the third and fourth constraints, now our nodal potentials come into play. So for every node of the network, we have nodal potentials P. And for every arc of the network, the incident potentials are coupled by a so-called nonlinear and in general non-convex potential function phi that depends on the corresponding arc flow. And of course, these potentials have to satisfy lower and upper bounds. And throughout this talk, we will consider potential functions of the following form, where depending on the constant R, we can model with this flow model gas, hydrogen, water, or lossless DC power flow networks. So what I really like about these potential-based flows is that we'll now do theory for this general flow model, and afterward we can apply our results to all these kinds of utility networks. And now we have the flow model at hand that we will consider throughout the talk, and we will move on to our robust network design model. And first, we're interested in the question, what network expansion are we looking at? And we consider a set of candidate arcs where we can decide that we want to build this arc or not, which is a discrete decision. So we have the decision x is equal to 1 means that we build this new arc, and then we have to enforce that the lower and upper potential, the lower and upper flow bounds are satisfied, and that our coupling between the potentials and the potential function is also satisfied. And if we decide to not build the arc, this means x is equal to 0. The arc is not existing, so the corresponding flow has to be 0, and the coupling of the potentials has to be redundant, which we ensure by big N's, and we have provable correct big N's. And in addition to the set of candidate arcs where we can decide that we want to build it, our approach can also cope with existing arcs. And for this, of course, our constraints of our flow model has to be satisfied. And when we all put this into one optimization model, we have our nominal model where we minimize the costs for building our new arcs. We have discrete decisions for building these new arcs, and then for a single demand scenario, we have to guarantee that this demand scenario representing the injections and withdrawals can be transported through the network, and this we model by our in general nonlinear non-convex flow constraints. However, this is our nominal model, so this network that you build only guarantees that you can transport one single demand scenario through the network. But usually these demand scenarios are based on predictions which are uncertain. And if now you have some demand fluctuations, this could easily render your computed network infeasible. So what the goal is for us is that we want to build a robust network that can take into account these demand fluctuations and guarantees that we can transport every demand scenario in our uncertainty set through the build network. And for this, we will consider an adjustable robust optimization approach. And we have a very general uncertainty set where we have all our demand scenarios that we want to consider, for example, different predictions for hydrogen. And we only have to guarantee that these demand scenarios are balanced. So this means that the total amount of injections is equal to the total amount of withdrawals for every scenario. But except of that, we can intersect this with any arbitrary compact set. So this means if you look at this uncertainty set, we can cover many different types of uncertainty sets, such as polyhedral, ellipsoidal, or even discrete uncertainties. So we can cover very different situations of demand uncertainties. And if you now put this all into one adjustable robust optimization model, we have the following challenging MINLP. We minimize our costs for building the network. Then we have our discrete X decisions, which are discrete here and now decisions that have to be decided before the uncertain demand realizes, because when you build the network now, you do not know the future demand, for example, for hydrogen. And then we guarantee in this robust model that for every demand prediction, demand scenario in your uncertainty set, which could be infinitely many, there exists a feasible transport through the build network, and this is a nonlinear, non-convex flow. So in general, we have an adjustable, robust, non-convex optimization problem that we want to solve to global optimality. And the question is now, how can we solve this challenging problem? Because of the non-convexity, we cannot apply any standard techniques such as based on strong duality. And our idea is now that we apply an adversarial approach. So this is a very well-known approach in robust optimization, especially in strictly robust optimization. And it works like the following. We start with a finite set of demand scenarios. Then we build our network with respect to this finite set of scenarios, which is then just a large MINLP, but it consists of finitely many variables and constraints. And then we fix this build network and ask ourselves the question, is this a robust, feasible network? So the question is, can we find a demand scenario in our uncertainty set that cannot be transported. If this is the case, then the network is robust and feasible. Otherwise, it is robust, feasible, and also optimal because we optimized it with respect to a subset of the original uncertainties. And so if we have no violating scenario, we terminate with an optimal robust network design. Otherwise, we add one of these violating scenarios to our uncertainty set and iterate again, which will lead to a different network design because the newly added demand scenario renders the old one infeasible. Sounds like a nice algorithm. It's very well known in strictly robust optimization, but for our adjustable robust non-convex optimization problem, there are two main questions. The first one is, how can we find a violating scenario for our problem? This is not an easy task. And can we guarantee finite termination, or will this algorithm iterate infinitely many times? But the main challenge here is really how can we find violating scenarios? And this leads to our main result. We provide now a novel characterization of worst case scenarios that verify robust feasibility for a given network. And we can partition these worst case scenarios into three different types of worst case scenarios. So the first type is only regarding the network structure. I will explain this in the next slide. The second type of worst case scenarios is about the worst case regarding the lower and upper flow bounds. And the third class of worst case scenarios is that these scenarios are the worst case for our potential bounds. And we have found polynomial many of these worst case scenarios that guarantee you robust feasibility for a given network or prove that this network is robust and feasible. And we now will have a closer look to these scenarios. So when we think about the algorithm, we now computed for a subset of our demand uncertainties a network. We fix this network, and now we ask ourselves the question, is this a robust, feasible network or not? And the first class of worst case scenarios considers the following, that we have unbalanced demands, which means that our network is directly robust and feasible. So what we do is, for every connected component of our network, we solve the following LP, which just looks in the uncertainty set for some scenarios, so that when you only consider this connected component, there is a surplus of demand. This means, for example, there is too much generation in this scenario, so that all things in the connected component cannot take this generation, and you actually have to transport it out of your connected component, which is not possible because there is no arc to the other connected components. So these are very simple worst case scenarios that do not rely on the underlying flow model, but if the objective value of these LPs is positive, then you directly know that your network is robust and feasible, and you have a violating scenario. And at most, we have to solve in the number of nodes many worst case scenarios of these type. So this was, I would say, the easiest worst case scenarios. And we now move on to the second and third class about the worst case regarding the flow and potential bounds. And here we have a very nice trick. So we again start with our network, we fix it, and we ask ourselves the questions, can we find a worst case scenarios that violates the flow bounds? And we first start with the lower flow bounds. So we are now interested in finding scenarios that violate the lower flow. And to do so, we solve the following optimization. So for every arc, we minimize the arc flow, and the constraints are mass flow conservation, the potential-based flow constraints. We optimize over our uncertainty set, but here is the important point. We do not consider flow and potential bounds. So at the first moment, this sounds counterintuitive, but actually we are interested in finding a scenario that violates the lower flow bound. So we cannot introduce this as a constraint, because then we will never find a worst case scenario with respect to this lower flow bound. But we can prove that if you solve this nonlinear optimization problem, and the corresponding objective value is lower than the corresponding arc flow bound, this is a violating scenario. And if the objective value is greater or equal to the corresponding arc flow bound, we proved that there cannot be any scenario in your uncertainty set that violates this lower flow. And with the same idea, we can check if we can find a worst case scenario that violates the upper arc flow bound. And if this is not the case, we know that there is no scenario that can violate the upper arc flow. So at most, we have to solve here 2 times the number of arcs many optimization problems. Then we compare the corresponding objective values to the arc flow bounds, and either we find a violating scenario, or we can guarantee that there is no scenario violating the lower and upper arc flow bounds. And with a similar idea, we can find the worst case scenarios regarding the potential bounds. So here, for every pair of nodes, we consider the potential difference, and we want to maximize this potential difference using our flow model, optimizing over the uncertainty set, but again, dismiss the lower and upper arc flow bounds and the potential bounds. And then we compare the objective value to some threshold values, and if they exceed this threshold value, we know it's a violating scenario. And if this does not happen for all node pairs of the considered network, then we know that there cannot be any scenario in your uncertainty set that violates the potential bounds. So here we have to solve at most quadratically in number of nodes many worst case scenarios for our potential bounds. And if we now summarize all these worst case scenarios in one complicated looking theorem, we have that if you give me a network and ask me the question, is this adjustable, robust, feasible? This is exactly the case if our worst case scenarios can be transported through the network, which we can check by comparing the corresponding objective values to some lower and upper arc or potential bounds. So now we have a very nice characterization that allows us to check with polynomial many worst case scenarios if a given network is robust, feasible, or not, which is one of the main ingredients for our algorithm. And this result holds for general compact uncertainty sets. So now if we consider the algorithm, we can apply it. So we start with a finite set of worst case, a finite set of scenarios. We compute our network, and then we can check robust feasibility by computing our finitely many worst case scenarios for this specific network. And if these scenarios can be transported through the network, we're done. It's robust optimal. Otherwise, we have violating scenarios that we add to our uncertainty set and start from the beginning. And since we are solving MINLPs, which are very challenging to solve, we only add the most violating scenario in every iteration. And finite termination directly follows from the case that we only have finitely many discrete decisions for our network design. And in every iteration, we cut off one of these network designs. So hopefully, I've now convinced you that this algorithm works, and we have a very nice characterization of worst case scenarios consisting of finitely many worst case scenarios. The question is now, how many scenarios do we actually really need? And I now try to convince you with 2 examples that in theory, we could need many scenarios, but this most likely won't happen in practice. I know it's just examples, but this is exactly what we discovered in our computational results regarding instances based on real-world networks. So here we have a simple network. We have one source, one inner node, and the remaining nodes are sinks. And we have an uncertainty set where we can inject up to 2 units of flow in our source, and every sink can withdraw up to 2 units of flow. And we can build for every existing arc an additional parallel. And when you now start our algorithm, in the first iteration, the worst case scenario will be that you send 2 units of flow, which is the maximum of the source, to the first sink, which can withdraw all these 2 units. And then this is a violating scenario for the existing network. And you expand your network by the parallel candidates and start with the next iteration, where you now send 2 units of flow, which is the maximum of this source, to the next sink. And then you have to expand the network, and you have to do this n times to get a robust, feasible, and then optimal network. And this example shows that in the worst case here regarding the number of scenarios, you need for this very simple example, number of sinks times number of source many worst case scenarios. And this can lead to a very large MINLP that you have to solve. The question is now, why do we need so many worst case scenarios for this example? And the answer is because we have a very limited supply capacity of our source. So this source can only supply up to 2 units of flow, which is the maximum demand of a single sink. But this is not realistic when you now think about, for example, a water network where you have a water reservoir. And this would mean that the water reservoir can only supply the demand, the maximum demand of a single household. It's more likely that this source can deliver the water to multiple sinks. So now we modify the exact same example with a different uncertainty set, where we say that the source can now supply much more. It can supply enough to cover the maximum demand of every sink of the network in a single scenario, which is often the case in practice. And when you now start our algorithm, in the first iteration, this source will supply to each of the sinks its maximum demand. You expand the network and you terminate after a single iteration. So this example shows it's not a proof because there can be more complicated network structures where this does not happen, but it shows that there are some subgraphs where when you have a large capacity for your sources, which is often the case in practice, you only need a very small number of worst case scenarios to cover all worst cases regarding the sinks. And this is exactly what we discovered in our computational results. So we applied our algorithm and the novel characterization for robust feasibility to apply this adversarial approach to some gas networks, where we have here a nonlinear and non-convex potential function. So we have a non-convex flow model, and we consider the gas lib 40 and gas lib 60, which have a few sources and multiple sinks. And we can build here in parallel new arcs to existing ones. And we have 2 versions of our algorithm. We have the plain version that I've explained to you, and we have an, I would say, enhanced solution technique where we add some valid inequalities of the literature and some convex relaxations to provide lower bounds to solve the MINLPs. But this is still an exact approach, so we never approximate during the whole process our nonlinearities. And we consider 4 different types of polyhedral uncertainty sets with and without correlations. And then we applied our algorithm to different use cases, and I will present to you now 2 different use cases. So the first one is that we want to robustify an existing network. So we have an existing network, we now have an uncertainty set, and we want to robustify it by building new arcs in parallel. And here we have our computational results. So above, we have our plane approach. Below, we have the approach with additional lower bound strengthening. And we see that for the gas lib 40 and gas lib 60, with both approaches, we can solve all different instances. But I would say the most interesting part is that we need only a very small number of worst case scenarios. So in addition to the single start scenario, this is not counted here in the tables, we only add up to 2 worst case scenarios, and still we can provably guarantee that the outcome of our algorithm is a robust optimal solution, guaranteeing that all possibly infinitely many other scenarios of our uncertainty set can be transported through the network. And this effect that you only need such a small number of worst case scenarios really relies on this example that I've explained to you, that you have in these utility networks only a few sources that can supply many things. So this is the first use case. And as you see with the runtimes, this is very effective considering the case that we have MINLPs. And now as a second use case, we have the greenfield approach, which now we design a network from scratch. So we have no existing arcs, we have nothing, and we want to build an entirely new network. And this is a much more demanding task from the computational point of view. So you see with our plane approach, we can only solve one instance for the GASLib 40 and GASLib 60. With our additional lower bound strengthening, it looks much better. If you consider the running times, we have a drastic increase to the use case of robustifying an existing network. But what we again see here is that we have a very small number of worst case scenarios necessary to solve these problems. Again, it's only up to 3 worst case scenarios that we have to add in our adversarial approach to obtain a robust optimal network, although we design a network from scratch. So to summarize, we have developed an algorithm to compute adjustable robust network designs for nonlinear flows and demand uncertainty sets. The key component is that we characterize finitely many worst case scenarios that can verify robust feasibility. We have finite termination for arbitrary compact uncertainty sets, and our approach performs very well in practice. And for future research, it would be interesting to extend this approach, for example, to include compressors or pumps in water networks, or to develop Venn inequalities for network design problems with nonlinear flows. And for this, I would like to thank you for your attention. And here's our recent preprint regarding the talk.